Hello, my name is Richard Gibbons, and today, oh, sorry. Hello, my name is Richard Gibbons, and today I will be talking to you about ASOM. ASOM stands for Analyzing Soil and Organic Matter. The mission was created by my group, Area 51. Let's move on. Now, the satellite is going to be built within a non-contaminant environment, meaning that the people building this will have to wear suits and the facility will have to be completely rid of microorganisms. It will be built with a geographic satellite camera and an astrospectrophotometer, an instrument that can analyze the hue of soil. The launch date is March 22nd, 2019, and hopefully there will be optimal weather conditions. Now, the satellite is going to collect data by using the camera to take a picture of a landmass, and then it sends it to the spectrophotometer, where it will be further analyzed. Then it will be sent down to a research facility on Earth to be further analyzed into the amount of organic soil. You see, we can use the specific color of the soil to predict the amount of organic matter. And then, once it's reached the end of its life, it will fall back into the earth, into the ocean, where it will be recovered. And as for information dissemination, the information can be posted on a few websites, one being the NASA website, and the mission can also be televised. Now, Delta II versus Antares. Now, Delta II, the thing is that it was built to carry the SMAP satellite, and since our satellite is similar to that of SMAP, Delta II would be perfect for this mission. Not only that, it's also a lot cheaper to build. In fact, Antares was $247 billion, versus Delta II, it was only $51 million. And the thing with Antares is that it's had a fewer number of launches. I mean, it's only had 5 launches total, and 4 out of the 5 it's been successful, versus Delta II, it's had 153 launches, and 1 out of 51 has had total success. Now, let me move on to the power and electrical subsystem of the satellite. Now, what this is going to have is going to have a rechargeable lithium-ion battery that will kick in case the solar arrays fail for some reason. And then comes the solar arrays. Now, this is going to power the subsystems, and it's going to be hooked up with solar concentrators to focus the power. And then we have the power control unit and the shunt regulator. Now, what these do is that they maintain a steady voltage and they maintain the amount of power within the circuit. And then you have the power distribution unit, and this will distribute the power to all the other subsystems, components, such as the inverter, the pyro switch, and the magnetic contactors. Now, the inverter uses DC and converts it to alternating current. And then you have a pyro switch, and what this does is that it acts as an emergency shutoff in case the satellite crashes for no good reason. And then you have magnetic contactors, and what these do is that they will control the amount of voltage from thermostats. Now, we will be getting into these later during this presentation. Now comes the control subsystem. This will control all the moving parts of the satellite when it's launched into orbit. So you have the onboard computer, which will control the solid rocket motors pointed in different directions. And so what this will do is that it will control the trajectory correction maneuvers, meaning that the satellite can, shoot itself one way into the correct path, in case it ever goes off path. And it will also control the geographic satellite camera, the spectrophotometer, and the reference gyros. Now comes the structural subsystem. This is where it sets up and goes into deployment. So you start off with the separation from the rocket, and then you move on to the solar array deployment. Now, for all these deployments, the geographic satellite camera deployment, spectrophotometer, and parabolic antenna deployment, actually for the spectrophotometer and geographic satellite, we decided to have the arms extend out just enough so that the instruments can't be interfered with the magnetic field that is being generated by the satellite itself. Now comes the propulsion subsystem. This is where the rocket goes up into space and then its parts separate. Now, the thing is that Delta II is a multi-stage rocket, so each stage is going to have different propulsion systems with different ways of stabilization. So for stage 1, we have a solid propellant combination. This is a hydroxy-terminated polybutadiene. It's a binding agent, which acts as a binding agent for the ammonium perchlorate. And what this will have is that it will have a spin stabilization. And this will reduce the amount of thrusters needed, which will lower the cost. Then you have stage 2. This will also have a spin stabilization, but it will have a monopropellant combination of hydrazine and iridium-coated pellets. And all this will be filtered through pipes. Then once that stage breaks off, you have the third stage. Now, it's the same monopropellant as before, except it uses 3-axis control and 6 degrees of freedom. This is where the TCM comes in, or the trajectory correction maneuvers come in. Then comes the communication subsystem. Now, this is where this will allow the satellite to receive data and send it back to Wallops Flight Facility or some other research facility. So pretty much what you have is that you have the control unit and the command detector unit being controlled by an onboard computer. And so then what happens is so now what you have is a communication subsystem, as I said before. So what is going to happen is that the Axis down converter is going to take the data and is then going to send it to the SX transponder, which is then going to send it to the SSA, and the SX transponder also sends it to the TWTA, and then both of those send it to the waveguide switches, and then that data is sent out through the parabola antenna, and then the data is sent back, and then it's sent back to the Axis down converter. Now we have the safety subsystem. And this is, I believe, the most important subsystem, because in case something were to go wrong while the satellite was in orbit and we would be able to do nothing, the system will kick in case something goes wrong. So now we have 2 further subsystems for this. We have a temperature subsystem and we have a hazard subsystem. Now, the temperature subsystem uses heaters, thermostats, like we said before, and optical solar reflectors to increase and decrease the temperature within the satellite. And then we have a hazard subsystem. Now, for this subsystem, it will have warning lights that will kick in or indicate when there's a broken circuit, or there's a fire, or a chemical spill. Now, if there's a chemical spill, then it will release another chemical with a higher acid on the pH, or is more basic to neutralize the spill, depending on what chemicals we're using. And now, how do engineers work with scientists? Well, in layman's terms, scientists give the constraints to engineers. So the scientists will tell the engineers, here's what we need, here's what we need to do, this and that, and then the engineers come up with something. Now, how do they react with technologists? Well, the engineers will build a rocket or build, they will build the rocket and build the satellite, and then the technologists will examine it, they will look through it, make sure everything's perfect, and then they will perform several tests on this. And here is my graphic, or my flowchart of all the subsystems, and this is pretty much everything we went throughout this presentation. Thank you.